So I wanted to use a different word, but I wasn't allowed. And you know how commercial people are. It's a little different world in the lab. It's a different world in the scientific area. But we are trying to turn the work that we do into more of a science. So on the bottling lines, we want to figure out how they work and then how to control them and to actually get the impact that we're looking for in reducing the amount of oxygen in the headspace, reducing the total package oxygen. And so you actually get that extension in shelf life. So this slide's all about just trying to convince you it's important. The headspace oxygen is important. And I guess you probably all are already convinced of that. You might not be here. I don't know. All right, so it all makes sense. You have faster rate of browning if you have a lot of headspace oxygen, loss of freshness, on and on and on. And then we have these prestigious researchers. I have quotes, including Stefan here. Talking about how important it is to shelf life, extending shelf life. And it all makes a lot of sense. The interesting thing is I talk to customers, and whenever they have a high headspace oxygen, they'll say, well, I'll take care of it by using a tin saran liner. And the analogy I use is the bull is already in the china shop, okay? Shutting the doors tight isn't going to help you much, all right? You like that one? So I'm in charge of the process improvement group, also innovation. And the process improvement team, most of the time we get calls when there's some desperation. If something's going wrong in the commercial process. They'll wait, they'll try to do whatever they're trying to do to make it work. And then they'll get things like caps blowing off bottles. So in an inerting process in our mobile bottling line, they got a new inerter. They had caps blowing off. And they weren't even measuring the headspace oxygen. So we decided, okay, yeah, it sounds like a good project for us to come in and help. And actually, a customer was asking for more control over that oxygen. It was very nice. Here's a picture of our mobile bottling line. Back about 5 years ago, we had one line. Now we have 4. One of the lines is actually a bag-and-box line, which is kind of unique. And then we have like special packaging. We have one line that's for like PET-type packages, spirits, that type of thing. So that's enough of the marketing. You see how spacious it looks on the outside, though, right? It looks pretty big. Once you get to the inside, it gets smaller pretty quick. And I'm just showing here the inerting system that we have. So here's the inerter. And it poses some challenges. Here's the capper head, and then the pathway of the bottle. We were limited on how far we could put that inerter in relationship to that capper. So that was actually a constant. And that's something that it's nice to be able to play with, but in this situation, we weren't able to. When we do our work, we have a number of platforms that we can use for modeling and for understanding how the data is impacting, or how the factors are impacting the responses. Design of experiment is one of our favorites. We can also use partition, which is a decision tree type modeling process. And you usually use that when you have a lot of data. You don't understand the factors very well, or you have categorical responses, those type of things. And then neural networks. And you can use neural networks in combination with partition. So if you have a process that's nonlinear, very strangely behaved, you can actually model it with a neural network, but you have to reduce the number of factors by using some technique. Typically, unless you have a really high-speed, high-end computer, you'd want to use partition first, get the factors that are important, and go neural network. This project that we were working on, it's a new piece of equipment. We didn't have much data except for verbal, and I think you probably see that a lot in your industry, or in your businesses too, where they won't collect a lot of data. You just hear stories, and the stories, caps blowing off. We don't know what's going on, type of thing. But it was a perfect project for design of experiment, a very structured approach. So here's the setup. We have our Cryotech inerter. You saw that in the last picture. We're using 30 by 60 screw caps, typical 750cc, 1680 GPI finish, very standard. And we were looking at controlling dose duration and the dosing liquid. We wanted to see what would happen using nitrogen versus argon. We also knew from some work we did that the headspace volume, as you're running commercially, it floats. We thought that might have an impact, so we included that as a noise factor in the experiment. The constants, and I have different colors here, and the constants, nozzle size and nozzle height are a different color because we actually did a pretest and found we should just hold those constant. The nozzle height didn't have much of an impact at all, and the nozzle size, we had to actually dial it down to where we wouldn't have problems with high headspace pressures. Inerter to capillary distance, you already saw we were limited there. We have to hold that constant. And then the bottling line speed, they want to run max. So we test max. Right? And our responses, so headspace oxygen percent. We're using the non-destructive, the fluorescence, the Anna Gret was talking about. The headspace pressure, it's important. You don't want your caps blowing off. And then the dosing liquid costs. And these, in the commercial environment, you always get these questions from the corporate people. How much more is it going to cost us if we use argon versus nitrogen, this type of thing. So we added that. We always like to have that in our quality responses. And so we went about creating the model. And here's the model fit for the headspace oxygen. On the x-axis, you see the measured headspace oxygen percent, and then on the y-axis, you see the predicted. Not bad. R squared, about 0.97. Like that? Yeah, so that's good. I mean, it looks like it's modeling pretty well. So what are the factors contributing to this model? Well, you can see here, dose duration is by far the biggest active effector, we'd call it. So that's what's really driving that response. The dosing liquid, argon versus nitrogen, you have maybe 24% of the responses due to that. And then our noise, the headspace volume, is about maybe, 9%? So it impacts. It's interesting. But it doesn't tell you the shape. It doesn't tell you much more than this is very important, focus on it. So the next slide will show you the same data in a different format. The biggest effector was dose duration. That's on the x-axis here on this graph. The second biggest was dosing liquid. And so we've separated the x-axis by category, argon versus nitrogen. And then on the side there, you see that legend. Oops. You see the legend. This is the headspace volume noise. And blue means the headspace volume was the lowest, and then the red means highest. So you can see the points that are higher are typically red, especially when you get into lower dose durations. And then the points that are lower are typically blue, and that's where that 9% came from on the headspace oxygen, on the headspace volume impact on the oxygen percent. Is that clear? So we did the same thing with the pressure, again in a nice model, measured versus predicted. We have more of a percent contribution, so the Pareto plot here, dose duration is still extremely important, but, the dosing liquid is even more important now. So the dosing liquid, if you're using, you'll see in the next slide, one of the liquids will cause more of a headspace pressure increase than the other. And then the headspace volume wasn't as important, so the variation in the headspace volume wasn't as important. And here's the same setup. Dose duration on the x, you got the separation argon, nitrogen, and headspace volume. And you can see, the reds are lower pressure, so the higher the volume, the lower the pressure. It's all making sense. That's good. But it's not as strong a relationship as you saw with the percent oxygen in headspace. So that's why it had less of an impact on that Pareto. But you can see the shape. You can see what happens. Argon is the one that really will drive the pressure versus the nitrogen. Okay. And here's a boring one. This is just a calculation, so R squared should be 1. So, okay, fine, And then just a sanity check, right? Here's a sanity check, making sure the headspace volume doesn't impact that cost. It shouldn't, it doesn't, we're in good shape. Here's the distribution of the headspace volume in cc's. And I just wanted to show you this because we're going to use it in just a second when we do a simulation. Okay, so just memorize this and help me out if I get lost. Okay? So, you see all these things going on, very dynamic. It looks like you got percent oxygen, you got pressure, you got the cost. I mean, what do you do with all that? And so what we do is we take all the responses and evaluate them simultaneously. Sometimes there's contradictions. You set the dose duration here, you're going to get great percent oxygen concentration, but you're going to have a really high pressure, for example. Or you're going to have a higher cost even though you have low pressure and a low percent oxygen. So there's trade-offs. And so when you stack them, I'll show you in a second what that looks like, hopefully. Yeah. You can actually see it all, and you can actually control that and get the ideal settings for everything as best as you can. So the next thing is, you have a model. Is it really showing what the real world is going to be showing you? Well, there's ways you can actually simulate what the responses will be real world better, and I'll show you that. And then, of course, you always have to do a confirmation. Models are never perfect, and sometimes you can be misled, so you always want to take the information you get from your modeling, take it to the real world, the commercial line, do what the model is telling you to do and see if it confirms, if it's actually predictive. Is it doing what you thought it would do, it's supposed to do? So let me try. This is where it gets dicey, right, Miriam? And so what I'll show you is we're going to model the percent headspace oxygen first. And you can see here, so this is the response we want to model. And these are all the factors. And you see it's not just 3 factors. We're actually looking at interaction effects between the dose liquid, dose duration. We're looking at quadratic effect. And we're looking at, they're all 2-factor interactions, all the quadratic effect that we can look at, which is where you got that curvature in some of the graphs. And okay, so it's going okay so far. And here you got it. So the model, you remember the R square about 0.97, you see it right here for the percent oxygen. And now we'll look at the profiler, which shows us each of the factors on the x-axis, and then the quality response, percent oxygen. Now, the interesting thing here is there is an interaction effect between the argon and the dose duration. And you saw that in the other graph, but you can really see it dynamically here. So as I go from argon to nitrogen, you see the percent headspace oxygen goes up. And the dose duration is more important to controlling that than the argon dose duration. You see that? Okay, that's all fine. But let's put it all together. So I'm going to stack all the responses now. All right, here we go. So here's percent oxygen, headspace pressure, cost. The x-axis, the same thing, argon, or dose liquid, dose duration, headspace volume. And we can go ahead and wiggle this back and forth now. You can see dynamically how it's affecting all of the other factors. You see? That's good. Okay, but now it's still not getting us what we need, is it? No. What we want to do now is tell the modeling software what do we want to target. So for example, headspace oxygen percent. We want to minimize that. And we want, let's say 5, which might be too high, but we'll just start there. Oops. The headspace pressure we're not too concerned with. Our caps can handle this range of headspace pressures. So we'll just say, yeah, let it ride. Okay, there you go there. And then you want to, of course, minimize your cost. Okay? Then you just say, look at all the combinations possible and give us the best you can give us. We're going to maximize the desirability. So it's telling us to use nitrogen. You see that? And use a high dose duration. We held this constant at the average, 19.53, because we don't control it. So this gives us an idea of what the average percent oxygen would be, 2.9. The average pressure, 13, not bad PSI, and then the cost per bottle. Okay. Now we're going to get fancy. Now we're going to go ahead and inject some real-world stuff into it. Remember the distribution we had before on the headspace volume? I've inserted it here. So I'm going to project that up through our modeling software. All right. So we have here 5% again. This is the same desirability functions we had before. I'm going to maximize desirability. So we get the same nitrogen, dose duration values. That's good. And let's say we wanted to simulate, let's say 12,000 bottles. So 1,000 cases. We can hit simulate. Now we have distributions, what we'd expect as we ran these 1,000 cases, what we'd expect in each bottle. The distribution on percent oxygen, the distribution on pressure, and this distribution is very boring because it's just 1 point. The cost, it's just calculated. Okay. Now, let's go ahead and take a look at that 10,000 bottle distribution. We'll look at both the oxygen percent and the headspace pressure. And there you go. We would predict, based upon this model, or these models, that we'd get about a minimum of a 1.1% oxygen headspace to a maximum of 2.9. And you see the distribution here? And then the pressure would be a minimum of about 11.5 up to a maximum of about 14, 15. So there's only one more thing I want to show you here. What is it? Okay, hang on. Which one? Yeah? All right, good. So now I'm going to go ahead and reduce that down. Say 5% is too much. And that distribution didn't satisfy us. Let's go ahead and drop that down to 2.5% headspace oxygen and see what happens. Okay, so now this is at 2.5 max. Now it's saying, okay, you got to go to argon. See that happen? And it's saying use, instead of the 70 with the nitrogen millisecond dose duration, you want to use about a 50. And the cost is a little bit higher, but if you're going to save, a half a year in shelf life or a year, what does that mean to you in return? That's something that should be calculated. We didn't do it here. So I can simulate again, and then we can take a look at the distributions and see where we're at. Wait a second here. I didn't save it. Okay. Let's take a look at the distributions of the headspace oxygen percent, headspace pressure. Okay, now it's saying we're going to go from about half a percent to about 2%. If we use the argon with that setup, and then we're going to go 15 psi to about 18. Still acceptable. So we're trying to bring science to the manufacturing floor. Sometimes that's difficult. You have guys out there just pound it out, just get the stuff into the bottle, get it into the case, get it out of my factory.
How about the cost, John? How did the two options compare the cost?
I could show you later. It's really, in my mind, it's insignificant. I'm sure in other people's minds, like the corporate types, it's not. Right? But when you're talking about the overall, because this is just a simple calculation we do on cost. If you looked at the overall use cost, when we were doing this work, we found that the argon in the dewar lasted longer than the nitrogen. So you really have to look at it more closely with maybe a financial person's help to figure out what is the use cost. But I could share with that later. I'm just trying to get through this French software little thing here. So that's all great, So we have it modeled. It looks pretty good. How do you deploy it? How do you get it to the operations floor where they can use that knowledge that you've just gained? It's one of the most difficult things to do. But what we've done is put it into like a graphical form, a graph form, where the people can just take a look at where to put the settings, or you can put it in a table type, a lookup table form, using the equation that you have for the models. Or you can actually just go ahead and embed it into like a spreadsheet or something, where they will just type in what they want, and out will pop the factor settings that they need to try to get there. And that's probably one of the best ways to do it. Now for the acknowledgments, thanks Stefan for inviting us to this, this event. Miriam Torreson, she's right up here. She did a fantastic job of managing this project about 5 years ago. And then our Vice President of Manufacturing, he's very, very excited, and he supports us strongly in sharing what we're learning, as long as it's not proprietary. So I just wanted to thank them all.